What's going on, guys? Welcome back to a new video. Today we're going to be learning about merge sort. Now before I get into this, I want to say if you're new to the channel, then check out the first link in the description. You'll find a guide on how to get your first tech internship or job if you're looking for one, and also some general tips for CS majors, or if you're looking to get into coding. I think that guide will really help you. But with that being said, if you're enjoying the channel, please subscribe, and yeah, let's get right into it. So, merge sort is a sorting algorithm created by John von Neumann in 1945. Merge sort's killer app was the strategy that breaks the list to be sorted into smaller parts, sometimes called a divide and conquer algorithm. In a divide and conquer algorithm, the data is continuously broken down into smaller elements until the sorting can become really simple. Merge sort was the first of many sorts that used this strategy, but it is still in use today in many different applications. So you have this, you'll keep breaking it down each bit by bit. You'll sort those bits and then you'll combine it back into the actual thing. Now, how to merge sort. So merge sort takes two steps. It splits the data into runs or smaller components and then recombines those into the sorted list, which is called the merge. Now, when splitting the data, we divide the output in our sort in half. When we recursively call the sort on each of those halves, we cut those halves into quarters. This process continues until you only are left with one single element. And then we begin the merging. When merging two single element lists, we check if the first element is smaller than the other element. Then we return the two elements with the smaller element followed by the larger element. And then merging. So when we merge the larger pre-sorted lists, we build these lists similarly to how we did in the single element lists. Let's call the two lists left and right. Both left and right are already sorted. When to combine them or merge them into a larger sorted list. Let's call it both. To accomplish this, we'll need to iterate through both sides with two indices, a left index and right index. So let me just say it in plain English because this is going to confuse you guys so much. So basically, remember in the last one, we broke it down into single elements, right? It's not sorted. You can see 98 is over here, 13 is over here, 270, right? It's not sorted. All we did was we broke it into single elements right here. Now, to put it into the sorted version, we take those, remember the thing that we saw in the previous slide, and we're just going to sort these single elements, okay? So 13 goes first, 98 goes next, 7, and then 2, 74, 12, and then 9, 81, and just 5 just follows through because, well, you have 5, right? Just one element. And then you sort these, and then you sort that, right? So 5 would go to the first slot, 12, and then 981, right? And then this gets sorted again, right? So this just gets broken down and then it just combines again into the bigger list with the sorted part. So you're basically just cutting it into half, sorting those halves, and then combining it, and then sorting those halves again until you create the larger one. Merge sort performance. Merge sort was unique for its time is that the best, worst, and average time complexity were all same, n times n log n, which means an almost sorted list will take the same amount of time as a completely out of order list. This is acceptable because the worst case scenario where a sort could stand to take the most time is as fast as a sorting algorithm can be. Some sorts attempt to improve upon merge sort by first inspecting the elements, looking for runs that are pre-sorted. TimSort is one such algorithm that attempts to use pre-sorted data in a list into the sorting algorithm's advantage. If the data is already sorted, TimSort runs at O to the n time. MergeSort MergeSort also requires space. Each separation requires a temporary array, so a merge sort would require enough space to save the whole of the input a second time. This means the worst case space complexity of merge sort is O to the n. Why does merge sort require so much space? And would it be possible to write an efficient sort that doesn't require any space? That's something to keep in mind of as we're going through this series. Now, let's go ahead and take a look at the quiz here. 7 questions. In the merge subroutine, how do we combine the two sublists into a single sorted list? By looping as long as both sublists has elements, comparing their first element, transferring the smaller element to a result list. By looping by comparing the first element with one of the sublists with every element of the other sublist and transferring the smaller elements by dividing, right? That is performed in the main merge sort function, not in the merge subroutine. So this is the merge subroutine. Okay, interesting. What is always true of the sublists passed as arguments to merge? They contain only positive numbers. They are not equal in length. They are sorted. They are equal in length. They're always going to be sorted. Merge sort will mutate or alter the original list passed as the arguments. False. Yeah, it doesn't change. It's the same list. It's just moved around numbers. What are the two steps in a merge sort? The split and the merge. What is the best case for merge sort when the function does not recurse? When the merge sort is passed an empty or single element as the argument, when merge sort has divided the list evenly, when merge sort is passed a list where the first element is less than the second element. I want to say where it's empty or a single list as an argument. Yeah, it's already sorted. Okay, what kind of algorithm is merge sort? It's divide and conquer. What is the time complexity of merge sort? It's n to the n log of n. Alright, and that'll end it right there.